we're going to be taking another look at the Fibonacci sequence through the lens of enumerative combinatorics. And the first way we'd like to approach this is by imagining organisms that are reproducing. So suppose you have a colony of bacteria. There are young bacteria, or immature bacteria, and there are mature bacteria. At the end of any day, any bacteria that was mature will create a young bacteria. The mature one is still there, it just creates a new bacteria which is counted as a young bacteria. But any bacteria that started the day as young will become mature at the end of the day. So any bacteria that was young is now mature, and any bacteria that was mature is still there, but it has spawned a new young bacteria. So depending on how many of each type of bacteria you begin with, can you predict how many bacteria you have after a few days? Like if you start with 3 young and 8 old bacteria, then after 10 days, how many do you have? So let's let m sub n and y sub n be the number of mature and young bacteria after n days. Okay, so m sub 6 would be how many mature bacteria we have at the end of day 6. And y sub 9 would be how many young bacteria we have at the end of day 9. Okay, then we can declare we start out with m sub 0 and y sub 0. At the end of no days, we are beginning with m sub 0 mature and y sub 0 young bacteria. Then we're going to set up some recursive relationships. Mature bacteria stay alive and young ones become mature. So at the end of the next day, how many mature bacteria do we have? Well, all the bacteria that were mature are still mature, but also all the bacteria that were young are still mature. So whatever bacteria, whether they are mature or young, the next day they'll all be mature. But only mature bacteria spawn young ones. So how many young bacteria do I have at the end of a day is how many mature bacteria I started with. So at the end of a given day, the number of young bacteria is how many mature ones we had at the start of that day. So suppose we begin with 5 mature and 2 young bacteria. How will the population progress? So here we have a chart. We're starting with 5 mature, so m sub 0 is 5, and we're starting with 2 young bacteria, so y sub 0 is 2. So at day 0, we have 5 mature and 2 young. So now let's figure out what do we have after day 1. Well, all the mature bacteria remain mature and the young bacteria become mature. So all 7 total bacteria that we had are now mature. But the only young bacteria we get are what are spawned by the mature ones from the day before. So y sub 1 is m0 plus y0. But y sub 1 is just m0. So these 5 mature bacteria spawn off new young ones, but whether they were mature or young, they will become mature by the end of the next day. So we keep doing this relationship. So the 7 mature and 5 young bacteria, well, the 7 mature bacteria are still alive, the 5 young ones become mature, but the 7 mature bacteria spawn 7 young ones. 12 plus 7 is 19, and the 12 mature bacteria spawn a young one. 19 plus 12 is 31, but the 19 mature bacteria spawn new young ones. 31 plus 19 is 50, and 50 plus 31 is 81. So here we have a chart of the first 6 days, how many mature and young bacteria we have. Can we figure out what's going to happen as time continues to progress? What's the relationship between all of this to the Fibonacci sequence? So here's a result. No matter how many mature and young bacteria we begin with, here were our recursive relationships. The number of mature bacteria on the next day is all the bacteria we had, whether they were mature or young. All the young bacteria on the next day, however, are only the ones spawned by the mature bacteria from the day before. So these were the recursive relationships we already had. Then here is the result. At the end of n days, we will have however many mature bacteria we started with times the n plus first Fibonacci number, but also however many young bacteria we started with times the nth Fibonacci number. This sum will give us the number of mature bacteria we have after n days. But also, the number of young bacteria after n days will be the number of mature bacteria we started with times Fn, plus the number of immature bacteria we started with times Fn minus 1. And just to remind ourselves, here's the Fibonacci sequence. F0 is 0, F1 is 1, and one Fibonacci number can be computed by adding up the two previous ones. Okay, so here's the result. We can prove it. It's actually going to be proved inductively, and it's actually quite straightforward. Okay, it is, however, a two-step recursion. Okay, the Fibonacci sequence appearing makes that not totally unsurprising. So we have two base cases to establish. First, day 0. Okay, if n equals 0, then the number of mature bacteria we start with is m sub 0 times f1, where f1 is 1, plus y0 times f0, where f0 is 0. So notice this term vanishes and m0 equals m0. Okay. But what about y sub 0? If we look at our claim up here, we would get y sub 0 equals m0 f0 plus y0 f negative 1. That appears to be a problem because the Fibonacci sequence, as we've worked with it before, doesn't ever have negative indices. We start at index 0, index 1, and then we move forward. But the recursive relationship can be used to work backwards. If I plug n equals 0 into this recursive relationship, we get f sub 1 equals f0 plus f minus 1. One Fibonacci number is the sum of the two before it. Now, if I solve for f sub minus 1, it's f1 minus f0, or 1 minus 0, or 1. So using the recursive relationship, we can actually find negative index Fibonacci numbers as well, in which case, right here, we get y sub 0 is m0 times f0. Recall that f0 is 0, so this term vanishes. y0 times f minus 1, and we've just computed f minus 1 to be 1. So again, we get y0 equals 0 plus y0. So y0 equals y0 is definitely true. We also verified that m0 equals m0 is definitely true. So when n equals 0, both of these claims right here, the Fibonacci form for m sub n and the Fibonacci form for y sub n, they both turned out to be true. For n sub 1, it's quite straightforward. Okay, so plugging in, looking up here, we would get m sub 1 is m sub 0 times f2, and f sub 2 is equal to 1. You can compute that here. Plus y sub 0 times f1, and f sub 1 is 1. m1 is m naught plus y naught. Well, that's just the recursive formula that defines the number of mature bacteria. M sub n is mn minus 1 plus yn minus 1. Okay. Also, y sub 1 is just equal to m sub 0. The number of young bacteria after the first day is however many mature ones I started with. But that's m naught times 1 plus y naught times 0. So the formula happens to work out for n equals 1 as well. So we've established our two base cases. Well, with our base cases established, we're going to go ahead to the inductive step. Assume that for all indices up to some capital N, the desired formulas work out. So for any choice of little n equals 0 through capital N, we get the predicted formula for the number of mature bacteria and also the predicted formula for the number of young ones. Then we're going to apply our recursive relationship for how to find out how many mature and young bacteria we have at day capital N plus 1. Well, capital Mn plus 1, the number of mature bacteria at the next day, was recursively defined as the number of mature and young bacteria we had the day before. Now m sub capital N, we've assumed will work out to this right here, which is going to be m naught times f capital N plus 1 plus y naught f capital N, and y sub n is going to be this right here, m naught times f capital N and y naught times f sub capital N minus 1. When I add these together, notice that I have m naught times fn plus 1 and m naught times fn. So I can factor the m naught out of those and get fn plus 1 plus fn. But I'm also going to have these two terms here, y naught times f capital N and y naught times f capital N minus 1, and I can factor the y naught out. So we have recursively assumed that m sub n is given by this formula with capital N's, and y sub n this formula with capital N's. When I add them together, I can factor an m naught and a y naught out of a couple of terms, but now observe that these two consecutive Fibonacci numbers add together to give me the next one, and these two consecutive Fibonacci numbers will add together to give me the next one. So indeed, the number of mature bacteria after day capital N plus 1 will match exactly the formula that we want at index capital N plus 1. This index is made one larger here and is not changed here. This index is made one larger here and is not changed there. So assuming that the desired formula holds for all indices up to capital N, we showed that the desired formula for the number of mature bacteria holds at day N plus 1. The number of young bacteria at day N plus 1 is even more straightforward. Okay. The recursive relationship was the number of young bacteria at day N plus 1 is simply equal to the number of mature bacteria from the day before. We inductively assumed that M sub capital N is given by M sub 0 F capital N plus 1 plus Y0 F capital N, right there, which is exactly equal to what this formula would predict if this index were capital N plus 1. M naught times Fn plus 1, Y naught times Fn. And that's exactly what we get. So having assumed that both of these hold for all indices up to capital N, then both of them also hold for index capital N plus 1. That completes the proof. Okay, we've inducted on two sequences simultaneously, but that is something you can do. Okay, so we showed that both formulas held for index 0 and 1. Then we assumed both formulas held for all indices up to capital N, and we're able to show that both formulas hold for index N plus 1. Inductively, then, both formulas always hold. So we appeared to be tracking two different things, young and mature bacteria, but one sequence was really controlling what was going on. The Fibonacci sequence times these fixed constants of the number of mature and young bacteria we started with. But this problem isn't so much about how Fibonacci numbers are incredibly special or magical. It's just that this problem was constructed to make them show up. The recursive relationship that gave us how many mature and young bacteria we have fundamentally dealt with adding together things from a previous step to get the next one. And whenever you do something like that, Fibonacci numbers are not a big surprise. In general, any sort of collection of objects, whether they be two things like mature and young bacteria or any number of things, but they obey some sort of interconnected linear two-step recursion. In other words, if I know how many of the objects I have at two steps, two consecutive indices, I can add them together and multiply by constants to determine how many I have at the next step. You'll always get what are called Lucas sequences, and the Fibonacci sequence is one special example. The Fibonacci sequence is often made out to be a very big deal. People track, for example, the appearance of Fibonacci numbers in pineapples and sunflowers and cosmic stellar arrangements, or who knows. It's really not magic. It's just what happens when the way something is arranged at two consecutive points in time can be used to determine how it is arranged in the next one. It's just math.